Assalamu alaikum everyone, my name is Hamid and we are a group 2. We are going to present our topic is Luminiscence Dosimetry. In slide 2, I'm gonna to explain the headline of our work. At first, I'm gonna to explain the introduction. Number 2, a type of luminescence dosimetry. Number 3, dosimetry properties. Number 4, advantage and disadvantage. Number 5 is the clinical dosimetry application. Number 6 is a reference. Slide 3 consists of an introduction. Introduction consists definition of the dosimetry and luminescence. What is meant by dosimetry is a dose measurement of the ionized radiation, while luminescence can be defined as a process of light emission. The phenomenon of thermally simulated luminescence, usually termed to thermoluminescence, which is TL. Optically simulated luminescence, referred to OSL, consists emission of the energy previously absorbed by a solid material in the form of the light during thermal or optical simulation. The emitted simulated light is usually different wavelength than simulating light. Slide 4 is continuous for introduction. The basic theory of TL and OSL is based on extensions of imperfection, impurities, defects, and otherwise ordered a crystal, which is give arrays allowed discrete energy level in the band gap of the crystal and may be captured electron or holes. Electron and hole pairs are produced by radiation throughout the certain fraction, reach for conduction, valence band, respectively. The trap of the electron and hole traps located in the band gap. TL without the trapped electron may be raised into conduction band and following their motion the conduction band recombine with the hole in a luminescence center and recombine with the yellow emitted photon. At slide 5, I'm gonna to explain type of luminescence dosimeter. At first, the first type of dosimeter, TLD, which is a thermoluminescence dosimeter, as shown in the figure beside my explanation. At first, the personal monitoring can be used in the same way of fact. They are common for whole body monitoring. They are often used radiation oncology, substance and the post properties of thermolysis are non-metallic crystal soils, usually powdered form. The second type of luminescence dosimeter is OSL, which is referred to optically simulated luminescence. Optically simulated crystal have been response to irradiation, as TLDS can be used similarly to personal radiation detectors. Further to the difference only of radiated mechanism. Number 3, these newly devices are usually activated to release the trapped electron when they are irradiated without travels or blue-green or infrared lights. Many of artificial material, such as porcelain and carbon-activated aluminum, which is Al2O3, also exhibit OSL properties. Slide 7 consists a continuous for slide 6 for the second type of luminescence dosimeter, which is an OSL. This material can be retained and record accumulated radiation for a long period of time. Furthermore, Al2O3, which is aluminum oxide, activated aluminum oxide, also has been made in dosimeter similar to TLDS and the foam pads are excellent monitor, and there are many applications are slowly replacing the foam and TLDS. In this nuance advance, the pacification of the ionized photon are beta particles.
Alaikum warahmatullah. Now we want to talk about how TLD and OSLD read out. As we know that TLD can stimulate by using heat, and as we showed in figure A, the TLD chip put on the heated band. The heated cycle in the heat band pass through 3 steps. The first step, low heat. The aim from the step is stimulate of the TLD, but the heat not enough to release the electron from a band gap. So we need to raise heat immediately to moderate heat. This is the second step. In the step 1 and step 2, no record any signal happened. The record signal happened in the step 3 when raised heat to the high level enough energy to free electron from the band gap of TLD. The luminescence phenomenon happen when the electron move from conduction band to valence band under effect absorb energy. The purpose of optical filter to ensure the photon of have homogeneity energy after the photomultiplier tube act as a signal amplifier. The photomultiplier tube convert the light to electron by photocathode. The number of electrons produced by photomultiplier tube magnified more and more until reach to photon anode to produce by strike electron under apply high voltage. This strike electron recorded as a count. The number count on a reader depend on how many light photon reach to photon multiplier tube, and by turn depend on how much dose on TLD. More dose, that mean more electron in band gap. Figure B present a typical configuration for an OSLD reader with the same step and same equipment, but the difference on how we can make stimulate. In OSLD case, we do not need to heat. Optical stimulate luminance dosimeter can be read using light, either of constant intensity, continuous wave technique, or variable intensity pulse technique. The OSL signal will decrease exponentially as the trapping center are emptied simplically. The trap can be calcified into 3 types: shallow depth trap that are unstable at room temperature, medium depth trap that may be released via exposure to light with a specific wavelength. The wavelength at range 525 nanometer, and green light from a laser or LED. The stimulate process called annealing. Okay. In the figure, or in this figure, explain how interaction between ionization radiation and electron band gap after the TLD exposed to ionization radiation as a dose, and electron gain energy from ionization radiation, the energy enough to make electron excitation and enough to eject free electron from valence band to conducting band. The electron inside valence band move to fill hole that produce by jump electron from valence to conducting band. However, the positive charge move in valence freely as electron move distance in the conducting band. Conducting band contain deep band gap trap, keep the excitation electron to next step. Next step, as we shown, the exposed TLD to heat. The heat act as a stimulate factor for electron in conducting band, and the amount heat enough to return the electron to valence band by emit light. That is called luminance. The emit light by this process equal to energy absorbed by exposure radiation. After this process, TLD become ready to use again to record absorbing dose. The OSLD readout process not much different as we mentioned before about TLD. The process excitation electron from valence to conducting band is same process with TLD. The electron in valence band after absorbing energy from exposure move toward conducting band. But the question is how electron return to valence band. The answer is when the electron exposed to light. Yes, light, not heat, and this is the main difference between TLD and OSLD in term method stimulate. Then, under exposed electron in deep trap of band gap, or may call analyte process, the electron move distance through conducting band, then jump to recombination center or other trap. During this jump, the electron emit light. This light represent luminance and represent how much this electron absorbing dose. There are many dosimetric properties such as fading, sensitivity, dose response, and energy depend. The fading term mean decrease in light output that occur between the irradiation and readout of a TLD. Some electron in a TLD material may have enough thermal energy to climb out of the trap even at room temperature. Fading is especially likely to occur in shallow trap with low energy requirement for electron release. As a result, the glow curve peak produced at low temperature. For example, peak associated with shallow trap should be fade the most. For more explanation, the theory say a glow peak half-life is a time it takes at ambient temperature for the area under the peak to decrease by 1/2 for LIF. LIF, by the way, this is the material made TLD. Okay, so as we shown in next slide, the figure represent relationship between count signal or glow signal of TLD and temperature. Okay, for example, if we have multiple peaks, 1, 2, 3, 4, and 5 peak, we study the effect time on the TLD associated with the shallowest trap has a half-life approximately 10 minutes to disappear. Peak 2 associated with the next shallow trap has a half-life of approximately 10 hours. Peak 3 has half-life of half year. Peak 4 have half-life of approximately 7 years. Peak 5 has a half-life of 18 years to an instant fading of peak 1 and to make them unsuited return dosimetry. Okay, this figure in the left showed LIF as we showing the figure represent a glowing curve produced immediately after the exposure. The curve on the right was produced 2 days after the exposure, not the complete disappear of peak 2. The figure in the right showed the completely disappear the peak 2. Light-induced fading can be concerning when TLD are used in environment dosimetry because of the possible exposure to instead sunlight and the long exposure period. Walaikum wa rahmatullah. Now we
Mu'min is talking. Dosimetric properties. The TLD and OSLD dosimeters are practical, accurate, and precise tools for point dosimetry in medical physics application. Fading, which can be defined simply as the spontaneous loss of signal with time, is one of the most important properties that a detector can have. The OSLD signal is plotted with respect to the delay time in the figure on the right, and it shows a small fading of about -1% per decade order of magnitude in time. A reproducible readout procedure, on the other hand, will reduce fading induced uncertainty. Furthermore, no transit behavior with the OSL has been observed, indicating that a stable OSL readout can be obtained immediately after irradiation. As a result, we can conclude that the OSL signal fading is small and there is no transit effect, allowing for prompt OSL readout after irradiation. Continue with the dosimetric properties. The sensitivity of a dosimeter is one of the most important, if not the most important properties that determine the field of application and use. The intensity of the emitted light per unit dose is defined as the sensitivity. The lower the absorbed dose that can be measured, the higher the sensitivity. The nature of the defect involved in the TL or OSL process affect the dosimetric properties of the TL or OSL detector, which are not solely based on the host material. The density, distribution, and energy depth of defect will have a direct impact on detector properties such as sensitivity, energy response, and linearity. This is most obvious when comparing TLD100 and TLD100H, which are both based on lithium fluoride, but have dramatically different sensitivity due to different dopant and trap structures. In regard to the beta particles, all TLD materials are very sensitive to beta radiation. Theoretically, we can say that all thermoluminescent material have the same sensitivity to the beta particle. In terms of photons, X-ray, gamma rays, the effective atomic number of the thermoluminescent materials is the most important factor in determining its sensitivity to the photons. The greater the sensitivity, the higher the effective atomic number. The effective atomic number is the number that tells us about the total number of electrons present in a complex compound around the central metal. Notwithstanding, sensitivity is effective by a variety of other factors, including the number of competing traps and the wavelength of the emitted light. OSLD sensitivity. OSL techniques are a better candidate for in vivo dosimetry in external beam radiotherapy than the TLD due to their unique dosimetric properties, which include a high sensitivity to both electron and photon beams, large dynamic range, good linearity, and post-irradiation stability. The raw measurement readings for the sensitivity test of 20 individual unscreened OCL dosimeters exposed to a dose of 100 centigrade are shown in the table. Based on the table result, individual OCL dosimeter sensitivity has a standard deviation of 7%. These findings clearly demonstrate that the dosimeter is extremely accurate and sensitive, and that the OSL reader system has excellent reproducibility. Linearity of the dose response of the TLD. The TLDs are frequently used in dose measurement due to their wide range of the linear dose response curve, their small size, and high sensitivity. The TLD dose response is defined as the functional dependence of the intensity of the measured TLD signal upon the absorbed dose. In the region between the minimum detectable dose limit and saturation level can provide knowledge about the dose linearity. These figures show the calibration curves of the thermoluminescence dosimeters exposed to the 6 mega electron volt electron beam in different dose range. Figure A 0 to 8 gray, figure B 0 to 10 gray, while figure C 0 to the 30 gray. The solid line represents the linear fit and the dot line represents the quadratic fit, while the next figures show the TLD irradiated by photons with identical parameters. From the calibration curves, it can observe that the fitting curve has linear behavior under the level of the 10 gray for both types of radiation beam. When moving to the higher doses, the quadratic model performs better than the linear model. For dose response data in the range of 0 to the 30 gray, a quadratic function fits the dose response better than a linear one for both photons and electron beams, which indicate that the feasibility of using TLD to perform accurate dosimetry in high doses region as required in non-conventional radiotherapy treatments. However, the calibration conditions such as field size, beam energy, angle of the beam incidence, and air gap may indeed affect the calibration curve and dose response. As a result, those factors and their effect should be assessed in order to obtain a more complete description of the TLD performance.
Good morning, everybody. Welcome in my presentation, Muhammad Al-Pakir Qasim. So the title of my presentation is Dosimetric Properties, TLD energy depends. So I'm giving you some definition, a brief summary about the definition about the dosimetric properties TLD. So the energy depends of the response of the TLDs employed were expressed as the radio of the response per unit observed dose for X rise of the quality Q and 60 coupled gamma rays. So the second premise of the definition, experimental values for the energy depends of the response of the various TLD photophores employed in the study were determined by radiations in NIST. So there's a just narrow spectra X-ray beams without air gamma rays. Well, the symmetric properties a TLD energy response. You can note in figure A shows 3 OSLD and TLD 100H and TLD 100 graphs of 10 real versus photon energy. While in figure B, these two figures can be used to compare the energy response quantitatively. So three dosimetric properties we have here. POSLD does response linearity in dynamic rate. So in this figure, This response curve for a 6 MV photon beam with a dose range from 50 SIGI to 800 SIGI. So demonstrate properties POSLD. I'm going to give you some definition about the energy demands according to OSLD. So energy demands of OSL detectors for photon beams of 6 MV and 10 MV and electrons beams with energy from 6 MeV to 14 MeV. The OSL responses are just normalized to the mean value of all the beams. 28 demonstrators were used for each energy. You can note that in this photon beam energy quality. So I'm going to illustrate the advantage and disadvantage of the TLD. In the beginning of advantage, we have the main resolvability, relative energy independence, and also accuracy and the precision. I mean the approximately 3 precision 100 for high dose. So also we have linearity in a wide range and tissue equivalent, small physical size, does rate independent. TL materials are available in many different forms. So directionally independent. Also I have a small sensitive volume independent of a pressure, no build up present. That's what I mean by the advantage of TLD. So and other side I have disadvantage. Well, the main disadvantage of the TLD, we have not recommended for beam calibration. Also readout in calibration time, consuming only one time reading during heating. So also I have lack of uniformity, energy demand, subject to fading, signal erased during readout, no preeminent record, accurate results require care superliner, and on the other hand I have no instant readout. So here is the advantage, disadvantage of OSLD. On the other hand, advantage, I will begin with a high sensitivity. This is the main advantage of the OSLD. On the other hand, I have high precision, size, confidence, readout flexibility, fast, non-destructive readout, narrow stimulating beams may allow us, no significant fading. I mean dust storage, so no need for a new line of what can be played and reused if needed. That's what I mean by advantage of OSLD. On the other hand, I have disadvantage of OSLD. In the beginning, in the main disadvantage of OSLD, I have sensitivity to light, not high sensitivity. So non-tissue equivalent, energy depends, only one material currently available. Only, I mean, one provide. So here is the application ATLD in POSLD. I mean the applications of TLD, OSLD. In the first, medicine, biology and related fields, reactor engineering, personal chemistry, and environmental monitoring. So here is in the upper of the paper, radiotherapy measurements and diagnostic radiology measurements. So my presentation that was according to these references, these authors and these names of his books and ATLC with other hand. So thank you for listening. Thank you for giving me the time. I appreciate your time. I have all the best for you and my brothers. Bye for now.